right? If your friends do it, you have to do it too. So be sure to handle the cases yourself. And so then I think we ran through stack frames already, but that was with the other examples. So here we can do it with merge sort. So what's a stack frame? It's a particular running of the program, right? It has particular set of variables, right, on a particular input. And so it gets its input. And remember what the box, that blue box is responsibility, the yellow guy. His job is to make sure that he solves his instance under the assumption that his friends work. Right? Everybody following? All right, so here we give half of the list to one friend, and that one friend says, great, we're under the assumption that friend's going to work. So what does he do? He gives us the answer, and then we get the input for the other friend. We assume that our friend will give us the answer, and then we merge the two together. That's what the stack frame does, right? Now, how does our friend actually work, right? Our friend is given a separate execution of it, right? He's given a separate stack frame. He's given separate local variables, right? So he's given his input, and his job is to ensure that he gets his answer subject to his friends working. So he gives half to his friend, who gives the answer. He gives half to his other friend, who gives him the answer, and he merges the two together, right? That's what he does. Everybody good? Is this too boring or useful? I never quite know where to hit that line. A little boring. We got a little boring here. How about other people? All right, well, we'll just zip through it here. A little boring. Now, we're going to put all the pieces together, right? So I'm given my input. I split the list. I get an input to my friend. And then I make a recursive call. And that creates a new stack frame, right? And so that stack frame has a friend, and he makes a recursive call, which gets a new stack frame. And that stack frame gets a smaller input, which he gives to his friend, and he makes a call, and so forth. And then this bottom guy, he just solves it himself, right? And then when that returns, it pops up, and I have the answer. Right, this guy has the answer, right? So then he gets his second friend, and he asks his second friend to sort, which is again a base case, so we come up, right? And now he can merge those two together to get a merged list, right? So now he has his answer, so he returns, and this guy back up here is starting running again. Everybody following this? Right? So then he gets his second answer friend, which calls and comes back up. And then he merges his two friends' answers together, and now he has the answer, so he returns it. Yeah? The top guy is which guy? Oh, he's the little house whose roof we take off. Yeah, exactly. So you just keep going through this. Right? You can see how fun it is to make PowerPoint slides. Right? Everybody kind of follow this? And then it keeps going like that. Right? Everybody good? So you certainly don't want to be describing that. Right? That's not how you describe what happens. So then there's the idea of a tree of stack frames. Come on, tree of stack frames. Oh, here they come. Right, here's the recursion happening. Right? And you get the tree. Right? Everybody good? Well, you have to make this, and then I don't know. I'm kind kind of addicted. All right? So what are we saying? We have this tree of stack frames, and each stack frame is responsible for themselves, right? But we put it all together using induction so that it works. All right? So, everybody get that? So we started talking about running time, and I think I muddled everybody. So let's talk about running time again. We're wanting to know, for in this example, how long it takes to merge in numbers, right? And we can give it a name. T of n is the length of time it takes to merge in numbers. And we want to know what T of n is and how fast does it grow. Insertion takes n squared time. Is merge sort the same? And so we can start looking at the code, right? How long does it take to split the two lists into smaller lists? Yeah, not very long, right? How long does it take to merge the two together? Probably order n time, right? This one here? Oh, no, because you had a line, and each step, you just looked at the first of both lists and have one guy go forward. Well, because it only takes me a constant amount of time to process one of the numbers, right? And I have n numbers to process. No, I have two lists. We're going to go through the code for it, but since I made this great animation, right, so where is the biggest number? It's at the end of one of the lists, but we don't know which. So we compared that these two numbers get compared, and the biggest one gets moved, right? And now the next biggest is one of these two numbers, so we just compare them, right? And so we're not looking at the entire list. To process one number takes us a constant amount of time. Does that make sense? So the whole thing is, right? I had to push my button once, right? I do a constant amount of work, push the button, and I move it once per item. So that's order n time. Yeah? Yep. And as a fact, as a general rule, I have this attitude, oh, coding's easy, so I won't give code. And if at some point people say, hey, you really should give the code for that, then I can do it. But it's kind of like pulling teeth a bit. All right, so here's pseudocode. We'll write the merging takes, order n time. And then, all right, where are we? Hello. All computers are slow today. Right, so his personal time, right, we're going to split off between how much time he personally spends versus the time for his friends versus his friends, right? So we need to know how long does his friend take and his friend's friends take and his friend's friends, right? We need to worry about all of those. Come on. All right, so now we want to know how long does this merge sort take, right? Well, what's the task there? Merge sort is, we defined here, T of n is the time to merge in numbers together, right? So here we're merging n of two numbers together. So how much time should it take? It should take T of n over 2 time, right? And so how much, and that's time for him and all of his friends, right? So him and all of his friends take a total of t of n time. And then the second guy takes another t of n over 2 time. Does that make sense? Everybody good? So here we get this recurrence relation, right? So it says the time to sort n numbers is 2 times the amount of time to sort n over 2 numbers plus order n. Right? That makes sense? And this is a recurrence relation, and we will learn how to solve it. You've already learned how to solve it, but it's later in the slides. All right? Why is the computer so slow today? Oh. All right. So here, we're going to do it. So one of the advantages of this tree is we can study for each box how much time does that box spend, and then we could add that up per layer, and then we add up the layers, right? So the first guy takes order n time, and let's ignore the order n because it's just some constant c times n, and that's the same c all along, and it's just going to confuse us. So at the moment, let's just say his personal time is n. So the next guy's time, right, is n over 2, because he's given only n over 2 guys, right? But there are 2 of them. So how much time for the total, that layer, right? That layer is, the total time is 2 times n over 2, which is n. Right? Everybody with that? And then the next guys, there are 4 of them, each taking time n over 4. And so the total time is 4 times n over 4, which is n. Right? And then the next layer, there's 8 of them, each taking time n over 8. Now it gets a little funny, as you know, if it was a power of 2, the n, then it would keep cutting in half. But since it's not quite a power of 2, some are going to finish earlier. But more or less, you can see that this is what's happening. Right? So it's saying that the time at each layer is n. Right? Each layer has time n. How many levels are there? There's log n layers, right, because we keep dividing by 2. Right? Number of layers is log n, so the total time is n log n. Right? And we ignored the big O at the beginning, so we put it back in. Everybody happy with that? And that's a recurrence relation that we were solving, and that's running time. Oh, and here's just the chart to warm up. It's just doing it again. We can talk about what's the size of the input. The size keeps going down by a factor of 2, right? How many layers are there? They're log n layers. How much work in a stack frame? Well, everybody's doing order how much the size of their input, right? If you're given an input of size this, then that's how much work you do, right? How many stack frames are there? Well, they're going up by a factor of 2, right? So then we multiply, and all layers are basically the same, so we do the adding and we get n log n. Everybody good? All right, so now we're going to talk about code, all right, because you know I love code. All right? So let's first think about I/O. One thing that amazes me when I actually have to sit down at a computer and write code, especially if it's a new language, I/O should be easier. I/O tends to be a pain. Where am I getting it from? Where am I putting it to? How are we storing it? I/O seems to be a pain. All right, so we have to think how we're going to input this list. All right? And that's our loop invariant, how the loop arrives, right? It arrives as a list, and then the postcondition is it leaves that as a list, right? And so that looked pretty good. However, here's a little issue, is how much memory do we use, right? we give an array with all the numbers, and when we get back, well, we want the sorted numbers to appear in the same array, right? We don't want a new array. So we say we're doing it in place. And so instead, we're not going to input a list. We're going to input an array. And then the post condition is that the sorted list will be in the same place. Right? Everybody good? So in that regard, we don't actually have to return anything because the outside world knows where the array is and will know the sorted numbers are there. All right? So now we want our friends to be able to sort an arbitrary sublist. Right? So we have to talk about how we're going to specify that sublist. And here's our, here, what's his guy? That's my, my friend is given a sublist, right? And the sublist will come, you have to think about how you're going to specify it. And we're going to specify it by naming a variable A and B, integers, and they're going to index, and the friend's job is to sort from A to B, all right? And what's his post condition? He leaves everything else the same. He just sorts things in that range. Right? Everybody good? Right here we're carefully defining precondition and postcondition so we know what's expected of everybody. Everybody understand the precondition and postcondition? Right? All right. So, of course, this is what I was saying. If we change the pre and postcondition for us, we have to change it, or for our friends, we have to change it for us as well. All right? So here's our new code. Now we're switching from this was our pseudocode. Now we're arriving to Java. All right, so our new code is going to have 3 inputs. It's going to have an array. It's going to have an integer A and B, right? And you'll note it returns nothing, right, because it's done in place, right? All right, so now let's start coding because we love coding. Oh, there's our little guy. What's he going to do? He's going to say, what is he given? He's given the entire list. Or I mean, actually, we don't know that, right? The array could be really, really big, and I'm not showing in the picture because we only care about the parts from A to B, right? I'm not saying that there's not an array on either side here, right? This is just his A and B, and we're focusing on that. All right, so this is me. I'm given my A and B. And the first step is we want to cut the list in half, right? Because we want to give half to one friend and half to the other friend. So we're going to calculate the integer that's in the middle, right? And so we're going to take the average of these two. So you add and divide by 2. And you might say, oh, well, that might not be an integer. But since m is an integer, Java will round it down for us, right? So that gives us an m here in the middle. Everybody with us? And then we have to sort the first and second halves. All right, so here's our friend. Our friend's precondition is what? What is he given? Right? He's given the same array. What's his A? It's my A. What's his B? It's my M. Exactly. Right? So here we call sort array AM. Right? Does it make sense? And we just imagine by magic that gets sorted. Right? Oh, here it goes. There it is. It's sorted. Right? And then what? Our second friend comes, and what do we give him? The array M to B. Do we want to go M? M plus 1. Exactly. We're going to go M plus 1 to B. Right? Because we don't want to give M to both of them. Right? Everybody good? And by magic, that happens, and then those are in place. Right? Everybody good? And then we want to merge the two together. So what do we have to tell merge? Merge needs to know the array. And merge needs to know A and M and B, right? So, oh, I made him a different guy because he's not a friend of ours. This is important. He's a nice guy, but he's not our friend, right? Everybody got that? Right? Because friends are recursive versions of ourselves, right? So I don't know who he is. Maybe he's the handyman that comes and helps us out, right? We have to pay him. All right, so he's given those, and what he returns, right here we're calling, I can't see it, but I assume you can see it. We get right. We give him the array in A and M and B, and what does he do? He merges the two together. Right? This makes sense. And that gives us, see, and then that is his postcondition, right? Which is also my postcondition. Is that making sense? So that's the code. Right? Everybody good with this code? So what are we missing anything? Base case, exactly. All right, so if the instant's small enough, you need to solve it on your own. What does that mean? Well, if the list is of size 1, you need to solve it on your own. Here's a list of size 1. What's our precondition? Is that we don't have to do anything. Or our postcondition is we don't have to do anything. A is indexing it. And what does B equal? Yeah, B is the same. Everybody got that? They're A and B are the same. Right? So we don't have to do anything. And because we don't have to do anything, we don't have to have any code. So we really only have the else. Right? So the else is asking, if the list is bigger than 1, then you have to do something. If the list is of size 1, then you don't have to do anything. And how do we test it? Well, B has to be bigger than A. Right? If B is bigger than A, then you do this. Right? Everybody good? Was this code good? Good to go over this code? All right. All right, so now we need to write the code to merge the two together. All right? So here's our little man, our green guy. His job is to merge them. Remember, that's what he does. And here we go, right? We have documentation talking about the pre and post condition. Precondition, it merges two arrays. The first subarray is in one. Those are. Yeah. See that one? That's not, I stole this from the internet, and that 1 is not a 1. What is it? No? It's supposed to be A, but they used, it's an L. Doesn't it look like an L to you? It's an L for left and right, and I thought that was dumb, so I changed it to A and B. So those are supposed to be A and B's. Try to remember to change them. All right, so again, we can't do this in place, right? I mean, before we wanted to do it in place, but now we can't do it in place. So the first thing we're going to do is we're going to copy out the subarrays, right? So the first subarray is going to get copied to a left thing, and the right subarray is going to be copied to a right subarray. And then, once we've copied them out, then we can merge them back in. Everybody good with that? So here's our code. We find the sizes of the two subarrays. Here we just do some math to say how many characters in their subarrays. And we allocate space for the subarrays, and then we copy the data out. And all right, so here, note that Java arrays are indexed from 0 to n-1. All right, so this here is going for I equals 0. People know this notation? A 4 says you start off with I equaling 0. And then you keep doing, and then you do this task. And then you increment, and you come back and you check this. And as long as this is true, you do this task and increment. And you do this task and increment. Everybody know that? All right, so here we're going to keep doing it as long as I is less than n1. Why? Because we don't want to access past the end of the array. And we keep incrementing, right? And what are we moving? We got to move this 88 down to here, right? So how do we move that 88? Well, in the left, here, I is indexing, that'll just be location I, right? Going from 0 to n minus 1 is I. And where's this guy? It's in the array at a plus I, right? Here you go, a plus the distance I. Everybody buy that? Yeah. So here that copies the left. We do the same to copy the right. Good? Holler if you don't get something. Now we have to merge the two together. All right? So here, this is what, remember, we had this great code. Here it goes, merge, merge, merge. Right? We do that. And then, I love loop invariants. Right? So the loop invariant says you jump into the middle of the code and you want to know what our data structure looks like. Right? And so we need to know that this is what the picture looks like, and we got to remember our places. Right? So how to remember our various, where do we need fingers? Right? We need a finger here to remember the top of this list, the finger to remember the top of this list, and a finger to remember where the next number goes. Right? So that's what I, J, and K are doing. Right? Everybody good with that? That's we state that in our loop invariant. Right? I and J index the next items in L and R, and K indexes the next location to receive an object. Right, so now we're at the top of the loop. You see here our brackets is our loop. We're at the top of the loop, and we need to maintain the loop invariant. All right? So what task should we do to maintain the loop invariant? Well, we've got to move somebody, right? We've got to make progress. Uh-huh. Yeah. Now, okay, first off, how do you know which one, who we're going to take it from? Exactly. And which one do we take? The bigger one. Bigger one. And where do we put it? Exactly. Oops, sorry. So we check to see if the number at Li is bigger than the number at Rj. And if it is, then we copy the number at Li over to the array at K. Right? So there it goes. And then, as said, we decrement I and we decrement K. All right? When I'm coding, I sometimes like streaming things because I want to see, what makes it. I mean, if it's too much code this way, it's harder to read. So anyway, it didn't fit on the screen, and that's why all these lines get put in one line. Everybody good with that? And so here we decrease those, and then we do it again. Oh, I don't actually know if Java can do this. C can do this. Can you do this in Java? It basically says, if you put the minuses afterwards, it says, do the operation with the values of K you have now, and then after you've done the operation, decrement them both. And if you put the minuses before, then it decrements first and then does the operation. It's in Java. All right, so there you go. You could do that. Otherwise, we we do the other guy, right? We move the guy in J over to K, and we decrement both. Right? Here we go. There, decremented. Everybody good with that? And then, so we keep going. We do it again. Here we go, that guy. And now, when do we exit? We have to think about when we're going to stop. And when do we stop? Is one of the numbers, one of the lists is empty. Right? So, if there's nobody in one of the lists, i.e., remember I is 0 is indexing the first guy, so that's fine. So when I is less than 0, then it's too small. Right? So if one of them's too small, right? So when do we do it? Oh, did we we haven't talked about this guy at the top, but he appeared anyway. We'll deal with him later, I think. So we keep going as long as both of them are bigger or equal to 0. Right? And when we fall out of the loop, right, this is afterwards, we're assuming that one of them's empty, but we don't know which one. Right? So what we'll do here is we'll just copy everybody in the L list over, and here we copy everybody in the R list over. And we know that one of those operations won't actually do anything because it's already empty, but that's okay. It'll do the other one. Right? Everybody good? Oh, here we got the beginning. Right? Now we have to say, how do we establish the loop invariant? Right? And we just put those guys at the right spots, and we're good to go. Right? Everybody good? Right? Here, this one's of size n1, so it's n1 minus 1 is the first guy here, and this guy here was our B. Everybody good with this code? And we did all of those things. And all right, so we've seen various ways of representing we looked at code that it has the pro that it's good for, you need it to actually run a computer, and the con is that it's a high level. I need a better way of explaining things. If I'm standing on a subway talking to you, don't give me code, right? And then we had the stack of stack frames, which is actually what the computer's doing, but it'd be crazy making if you try to explain it, right? We've got the tree of stack frames, which views the entire computation. It's good for thinking about the running time, but it's just too much. And then we have our strong induction, which is you worry about one step at a time, and the negative is that you have to trust. Everybody got that?